Okay, so continuous normalizing flow part two, we're gonna jump right in. I'm not gonna do any review of what we did the last time. This is just a continuation if you wanna know where we left off, or if you wanna know where we stopped, just watch the first part. So, okay. Last time we took the derivative of log density with respect to time. So last time we took the derivative of log density with respect to time, and we ended up getting this. We solved it all the way down, but as part of the simplification, as part of the derivation, we saw that the partial derivative of log density with respect to time was equal to this simplified form of the continuity equation. So now we're going to discuss that part. Actually, so before that, I wanted to discuss a different image. So last time I had this image where I tried to simulate a color spectrum by using these discrete overlapping color circles, and I tried to use that to model density. And I just realized it might be easier literally to just put a bunch of dots on this plot and then model density that way. So these are time steps, time step 1, 2, and 3. So this is the state of the density field at these different time steps. And you can imagine that these particles are moving in this direction, okay? You can almost imagine it like, you can think of it like you have a candle lit, right? And then you blow out this candle. And it's like the candle has various, right? It's like smoking up. And in some places, okay, I don't know why my iPad is doing this. In some places, it's a bit sparse, but in other places, it's really dense, right? So when we're talking about this density field, right? And specifically, we're talking about this continuity equation, so the conservation of mass equation, which I'll talk about in a little bit. You can think of this, right? So we're borrowing these equations, right, from fluid dynamics. Now, so essentially you can think of this as a fluid, but don't think of it like water. Think of it as a compressible fluid. So a compressible fluid, the density can change. Water, the density, I don't think the density of water can change at all, maybe under very extreme conditions, but most fluids, the density cannot change. But when you think about fluid as a gas, because gas is a fluid, right, then it's a compressible fluid. So I want you to think about this density field, right, as a compressible fluid moving through space, okay? And the velocity for this in this diagram is in this direction, right? So I'm just, and then another way you can think of it is when you blow out a candle, how the smoke is kind of dense in some places and then it disperses in other places, and then it kind of, and then they go and they intertwine back in with each other and they become more dense, right? But of course, in our case, where the direction is oriented slightly different, so it would be like this, right? But you can still think of it as a candle being blown out, okay? And so across time, if you pick out a point, so I think I described the Eulerian point of view last time. I don't remember if yes, I did, because I discussed the total derivative. So if we pick out the same point, right, and you imagine you are a fixed observer at this point, not a particle, just you are an observer, just an observer, right? The Eulerian view is imagining how the density, how the particles are flowing past you at this point, right? And then the Lagrangian view is you are a particle along a trajectory, right? You can just imagine yourself being this particle at different states, right? And then you're seeing how the density, right? So the density here is pretty dense. The density here is pretty dense, right? And then it's a little bit less dense here, right? Or maybe we can actually, let's modify this. Oh. Right? So it's pretty dense here, and then it's less dense here, and it's a little bit more dense here. That's because, you know, this is a compressible fluid, and at each time step, the density of the whole entire field is changing in different points. Okay? So that's what I was trying to explain with this diagram, but I realized I could model it a bit better. So, okay, right. So we were talking about how we arrived at this conclusion, and we wanted to explain how this is the continuity, how the continuity equation simplifies to this, which is what we swap into here. Okay, so how do we get the partial derivative of log density with respect to t? Remember, before we were calculating the total derivative, so we're just calculating the entire derivative of log density with respect to t, which that means we have to account for we have to account for partial derivative here, and then we have to unpack this function too. So it's partial derivative with respect to x and partial derivative with respect to t, right? But then we have to use the chain rule and do the derivative of this with respect to time. That's how we get the total derivative. Now we're looking at the partial derivative of log density with respect to t, right? Which is a term inside of this total derivative. So, okay. So we look at that, we look at the partial of log density with respect to t, and we're like, oh, well, this is just the continuity, this is the conservation of mass equation in continuous time. So it's called the continuity equation. So it basically says mass cannot vanish or disappear. What that means is that the total amount of particles across state is the same. New particles do not disappear or leave, right? They just flow. It's a compressible fluid, so the density changes and they just flow in this direction, right? Imagine this is a window, right? This is a window, and then we have our liquid is all around and just passing through this window, right? So rho is density, t is time, and v is the particle velocity field, right? So rho is density at point x and time. Rho is density at point x and time t, and v is velocity, particle velocity field, right? So if you put in a position and a t, it gives you the instantaneous velocity of a particle at that point, right? So if you just put in a spot on this map, it says this is what the instantaneous velocity of a particle at this point is going to be. So if you think about it, it's saying the right side of this equation, which is called the divergence of flux, right? It's basically saying it's describing the flow of mass, right? You have velocity times density, which you can think of it as the flow of mass, right? And if this term, if the entire thing, including the negative, is evaluated to be negative, that means that it's in a state of convergence, right? So it's in a state of negative divergence, which is a state of convergence, which means mass is flowing in, right? So that means that the local rate of change of density is negative, right? So if density is decreasing from this locality, that means mass is flowing out. And if the local rate of change of density at this locality is positive, that means density is increasing, that means mass is flowing in. So, okay. So now we actually calculate what this partial derivative is. So now we just substitute, right? So in our case, rho is P, is probability density P, and V is what? Let's go to my other notes. So part one notes, V is our ODE, our vector field, right? Our neural vector field, F, right? And so I'm just writing this using our variables here, okay? This is just solved differently up here. You can forget about this. So we just start performing derivative operations, right? So by the chain rule, this becomes this, right? And then we take the partial of log, which becomes this. The derivative of log is this, with respect to t is this, right? And then this is this. So we just swap it in here. I bring the negative outside. And then this, by the product rule, if I distribute this, right? What is this? This is a vector of differential this gradient, this nabla acts as a vector, and this is a dot product, right? This is a vector this is a vector of gradient differential operators, right? It's literally a vector of partial derivatives. So by the product rule, this is just vector calculus. By the product rule, this is equal to this. And then we just bring this through. This cancels. We write it down here. And then this term right here, right? Basically, if you look at this, by the chain rule, if you look at this term, the nabla x log density by the chain rule is equal to this, right? So this equals this. So then I just swap that in there, and then we write the whole thing, which is this right here, which we swap into here, and then we continue with this derivation to get the final form of our total derivative. Okay, so the final form of our total derivative, so we're basically saying the total derivative equals the negative divergence of the velocity field. This is not divergence of flux. The divergence of flux is a measure of the flow of mass, right? It's velocity times density. It's the nabla it's a gradient operator times density dot product with density times velocity, right? This is a gradient operator dot product with a vector, a velocity vector, right? So the instantaneous, this is called the divergence, and it's a measure of how your velocity is expanding or contracting at a locality. It's a measure of are your particles, are they spreading out at a point, or are they converging? Are they contracting at a point? So, and I'm gonna explain this, right? So this is what we're gonna do next. So, okay, I'm gonna show you how that equals what's called divergence, and that which is equal to the trace of the Jacobian, of this Jacobian matrix. Okay, so what is the Jacobian? If you remember from discrete normalizing flow, the last topic I covered, the Jacobian is, it's a linear approximation of f. So if we have a map f that takes vectors, that maps a vector to a vector space to a vector space, the Jacobian is a linear approximation of f around a small neighborhood of x. Okay, so if we have a point x and we take a small infinitesimal neighborhood around it, right? The Jacobian is a linear approximation of the map f around that point. What that means is that I think the intuition is captured well by this equation. It says f of x plus delta x is approximately equal to f of x plus the Jacobian times delta x, right? So in two dimensions, if we have this function f of x plus delta x, right? If this is x and this is delta x, f of x is here, then f of x plus delta x can be the Jacobian can be used to approximate f of x plus delta x. Now, of course, we want this delta is really an infinitesimal change in space. It's not, the greater your delta is, right, the further off your approximation is going to be, okay? So the Jacobian is a matrix, right, such that when we multiply it by this delta vector, we get another vector that we can add to f of x here. So the Jacobian is a matrix where each element is a partial derivative, described as you can see described here, right? So we write the Jacobian can be expressed like this, where we just write it as a partial of f with respect to x, where f of x, right, and x are both, they're both vectors, right? So we know that we can, so we call it a matrix where the entry ij is how much the ith velocity component changes when you nudge the jth coordinate, right? So I just wanted to do a very quick edit to explain the geometric interpretation of an entry along this axis, entry ii. So remember, this is the partial derivative of velocity with respect to change in position. So this isn't like discrete normalized flow where we're looking at the partial of a coordinate with respect to a coordinate. This is we're looking at the partial of velocity with respect to a coordinate. So this is saying as we move along an axis, as we do a tiny nudge in position, how does the velocity change relative to that nudge, right? So if this value is positive, that means that we have velocity of some magnitude of particles are expanding away from each other, right? So that means the density is decreasing. If an infinitesimal nudge results in a negative value, that means particles are moving towards each other. And that means that density is increasing. And remember, we're talking about the Jacobian, right? So it's a linear approximation. It's a linear approximation for a small neighborhood around an input x, a small neighborhood, right? An infinitesimal neighborhood. So that's why we know, this is why we know the behavior of the particles around x, right? It's not just for, we're not just talking about a point x, we're talking about an approximation. We're talking about an approximate velocity for a small neighborhood around x. So for a small neighborhood around x, right? Let's just expand the neighborhood, right? We can, whenever we want to understand the behavior of something, we can take it in the extreme, right? So we're just going to expand the neighborhood and make it larger. We're just talking about what happens, what's the velocity for particles in that neighborhood, right? And if it's negative, that means we have inward movement. If it's positive, we have outward movement. And then the trace, if we sum all these values, if it's positive, that means that the volume is expanding and the density is decreasing. If it's negative, that means the volume is contracting and the density is increasing. So that's how you interpret this Jacobian, the entries along the diagonal. Okay? And so now, so that's the geometric interpretation of the Jacobian. Now, bringing it back to the derivative of our log density with respect to time, right? It equals this. Remember, this is a vector of differential operations, right? Such that nabla times f, which is also a vector, right, is equal to this sum. It's just the dot product. That's all we're doing, right? This is a vector. Remember, x is a vector of differential operations, right? It's a vector of partial derivative operations. F is also f of x is also a vector, and the dot product gives us this. So this is equal to this, right? I, which is the trace of the Jacobian. So that's how the derivative of our log density with respect to time of a position along the trajectory is equal to the negative trace of the Jacobian, which gives us a measure of expansion. It gives us a measure of expansion and contraction. So that brings us to our final step. Now that we have the derivative of log density with respect to time equals the negative trace of the Jacobian, we use the fundamental theorem of calculus to get our instantaneous change of variables in continuous time, right? This says if this is an integral f, so if the derivative of capital F is equal to little f, that means that f is the antiderivative of f. So that if we're evaluating this integral from a to b of little f, then capital F of b minus capital F of a is equal to this integral. That's the fundamental theorem of calculus. If we're using Leibniz notation, right, which is the notation we're using, it's dy, it's a derivative of y with respect to t equals gt, this function that we're evaluating in the integral. Then we can say this, y of capital T minus y of 0 equals the integral from 0 to t of g of t dt, right? Now, this is this side of the equation is the derivative of our log density with respect to time, and the right side of the equation is the negative trace of the Jacobian. So now we use the fundamental theorem of calculus to write this, and we can just solve in either for either log density, right, to get our instantaneous change of variables in continuous time. So that's our, and then we minimize this is our likelihood, right? We minimize this negative log likelihood as our training objective. Or to write it in terms of maximum likelihood, we can just write it like this, right? The expectation under our data of the log density of the log density. So just to mention, the problem with continuous normalizing flow is the trace is a computational bottleneck. The solution is to use the Hutchison estimator, which I'm not going to go over, but the problem is that it's still expensive, which is why we're going to move to rectified flow next. So one last thing to cover is training. It's not so obvious actually how to train this. So essentially what you're going to do is we're going to start by taking a sample of our data. We're going to take a sample image x naught, right? And right, okay, remember, we want to calculate this. We want to get some estimate for, we want to use this to get an estimated, we want to use this to get the log likelihood of a data point of an image x naught from our of a training image x naught. So to get that, first, what we do is we sample an image, and then we need to get the image in our we need to get the corresponding image from our base distribution, which we assume to be, in our case, we're going to assume our base distribution is distribution is a standard normal, which I would also do if I was coding this up, right? So first we need to push x naught along this trajectory to get the corresponding image vector from the base distribution. To do that, we need to solve this equation, right? We have a vector field initialized to be, let's just say we just initialize it to be theta to be random at first. So this is parameterized. This is a neural network parameterized by theta, right? So integrating this is our differential equation. If we remember, this is a vector field. What we do is we input, we're going to input positions along this directory and time steps, right? And we're going to get back a vector, right? We're going to get back a vector that's tangent to this trajectory. This trajectory doesn't actually exist, right? What we do have is a vector field, okay? So this is a vector field, right? So essentially what we're going to do is if we solve this integral, right, we're in PyTorch, we're going to use a ODE solver, right? And we're going to numerically integrate using that ODE solver we're going to numerically integrate this integral using an ODE solver, which is essentially going to, right, it's like in the discrete normalizing flow, right? We're essentially like how we would compose maps together and then apply them to X. We're basically doing that in continuous space. We're just getting a bunch of vectors tangent. We're getting a bunch of vectors, and at each infinitesimal time space, we're just nudging our data point, our vector, our original image vector, right? Such that by the time we're done integrating, we've basically carved out this trajectory. So we numerically integrate with an ODE solver, and then we add that to x naught, right? So this gives us a vector. We add that displacement to this vector, and then we get x sub capital T. And then, right, we're trying to solve this equation. So now we now have x sub capital T. Now we just calculate the density, which we know how to do because we've assumed this to be a standard normal. So now we calculate the log density, okay? And then using the same ODE solver, right, we calculate this integral. And then we subtract that result from the log density, right? Which basically says, however, this is saying, however your original log density, right? However you've expanded or contracted from your original point in order to get the density here, you need to subtract that. So let's say you've expanded from this point to get to here, right? So that means the original density is going to be smaller. You need to subtract that expansion from here. You need to subtract the amount you've expanded from the density that's here to get the estimate of the log density of your training sample. So yeah, you compute this likelihood and then you backpropagate. And that's continuous normalizing flow. There you have it. So let's do a review. I'll review both of them together, right? So starting from the first notes that I have. So continuous normalizing flow. We have an image x naught, a sample from a corresponding vector from a base distribution, a more simple base distribution, x sub t, where the goal is to turn this simple base distribution into a more complex image distribution. We have this instantaneous change of variables in continuous time, where this is the Jacobian, this term inside of the trace is the Jacobian of f, where we have a neural network that parameterizes the vector field. So this differential equation describes the vector field that continuously drags a simple distribution into a data distribution. And this is our likelihood. So what that means is we essentially learn a vector field such that if we were to sample a bunch of time steps in between 0 and t and compute and pass in the position and the time step, we would get a bunch of vectors, a bunch of velocity vectors tangent to this line. And that's how we push x naught to xt. Now, to actually get the instantaneous change of variables formulation, essentially first we take the total derivative of our log density, and that coupled with the conservation of mass in continuous time, the continuity equation, which is the partial derivative of our log density with respect to time, we compute to be this. We use that in our total derivative of our log density to eventually bring it to this, which is the divergence which we calculate upon observation. We see that it's equal to the trace of the Jacobian, where we now understand that the geometric interpretation of the Jacobian is a linear approximation of our function f around a small neighborhood of x for an input x, right? Where f is a mapping between two vector spaces. So our Jacobian, if this is a nice definition of our Jacobian, we can see that, which is basically that if we want to, it gives us an approximation for f. So f of x plus delta x is equal to f of x plus the Jacobian times delta x. That means that our Jacobian, the values of our Jacobian matrix must somehow capture the behavior of F in a small neighborhood. And it does. We've basically shown that geometrically the entries of the Jacobian show how much the ith velocity component changes when you nudge the jth coordinate. This is our total derivative. We have this nabla, which we established that our nabla is a vector of differential operations, right? These partial derivatives. So the nabla dot product with our neural network, our velocity vector is equal to this, right? Simple dot product. Well, we see that this is equal to the trace of the Jacobian. So we say that the total derivative is equal to the negative trace of the Jacobian, which is basically saying our density, it's saying how is our density, what's the instantaneous change of density with respect to time. We're saying it is, we can measure that by, we can measure that by understanding how our velocity field is expanding and contracting. And we say, okay, that's really cool. Well, how about we just do some Calc 101 and use the fundamental theorem of calculus to write our objective like this. And then we can solve to get our final objective, which when we train, we make this a negative log likelihood. And we showed that to train in PyTorch, we get an ODE solver. First, we take a training sample and we want to push it along this trajectory, which doesn't actually exist, but what does exist is our neural differential equation, our vector field, our velocity field, parameterized by theta, which basically says, it gives, if we were to sample a bunch of time steps in between 0 and t, right, and then pass in the position in the time step here, we would get a bunch of velocity vectors tangent to this line. And that's how we push this flattened image vector to this vector in our standard normal. We use our PyTorch ODE solver to get this integral. We add this displacement, this offset to x naught, and we get x sub t. And then we use that same ODE solver to get our density, our density offset, if you will, right? So now that we have x sub capital T, we know that it's standard normal, so we can calculate the log density, and then we need to calculate the integral of the divergence, which is the trace of the Jacobian. So we say, okay, we have xt. Now we get some continuous measure of how our volume expands or contracts, which, because we know that mass cannot be created or destroyed according to our continuity equation, and according to our continuity equation, we're getting some measure of how flux, of how mass is moving in and out of an infinitesimal volume, right? An infinitesimal volume, which is represented by a locality along our trajectory, right? So, and that basically, and that, ladies and gentlemen, is continuous normalizing flow. That's a hard topic to grok. At least it was for me. I really enjoyed the process of coming to understand this, because I got to look at differential equations again, which is a class I took 18, 19 years ago I got to look at multivariable calculus again outside of, standard neural networks. So this was really fun. I hope that me breaking this down gives you some intuition on continuous normalizing flow. Next, we're going to move on to rectify flow. And it's much more simple than continuous normalizing flow. If you can grok CNF, you can easily grok, let me not say easy, I don't like to use that word. If you can grok CNF, then you can grok rectify flow. And then after I show the objective function for rectify flow, I'll start coding up some image generation using rectify flow. So yeah, I hope you enjoyed. Feel free to ask any questions. I'm going to upload part 1 and part 2 notes. Yeah, later.